Welcome back, everybody. Time for yet another of your favorite chemistry videos. Today what we are going to briefly talk about is something pretty simple. We are going to talk about types of chemical reactions. So you've learned what they look like. You've learned how to balance them. Today is being able to look at them and kind of categorize them into one of 6 different types. Now there's more than this. It is not really just 6. But for the scope of our class, we are just going to focus on 6 of them. So moving on, let's see what we can do here. Okay, so starting with the first reaction type, and this will sort of follow along with your PowerPoint, so if you have that in front of you, that might help. The first type of reaction we're going to look at is called a synthesis reaction. Word synthesis means to make something, so that's literally what we're doing. You're putting 2 things together to make one. Now, that can be 2 elements, so calcium plus oxygen makes calcium oxide. Okay, obviously we'd have to come back and balance it, but that is a synthesis reaction. You have 2 elements on this side, and the really big thing to notice is there's only one product. That's the key to a synthesis reaction. It can be compounds. Now, you're not going to see a lot of these in this class, but you can take 2 compounds, okay, sulfur trioxide plus water, you can make sulfuric acid, okay, and that's a synthesis reaction. Okay, 2 individual things coming together to make one. For the record, it doesn't have to be 2 reactants. It could be 3, it could be 12, it could be 80. The kicker with a synthesis reaction is there is one product at the end. So something cool you can do with synthesis reactions is now that you've learned about your ionics and your covalents, you can actually predict the products if I give you 2 reactants. We haven't gotten into how to do it if there's 2 compounds, but if I give you 2 elements as reactants, magnesium and nitrogen, you should be able to tell me what they make knowing that it's a synthesis reaction. Now, what everybody wants to do is just say, oh, put Mg and N2 together, you must get MgN2. And that's wrong, because what do we have to do every time we put a compound together? We've got to consider the charges. So if we look at magnesium, magnesium has a charge of 2, nitrogen has a charge of 3, so this is a synthesis reaction, okay, magnesium plus nitrogen, but your end product is Mg3N2. And then, of course, you would have to come back and balance, okay, which we won't do in this video. So that's an example of a synthesis reaction. Easy. Second type of reaction we are going to learn is called a decomposition. And this is also easy because it is the exact opposite of a synthesis. If something decomposes, it falls apart, it breaks apart. So synthesis had one product, decompositions have one reactant, and that reactant breaks down into its parts. Okay, so salt can break down into sodium and then chlorine, which is a diatomic. And again, I'm not going through and balancing all these just in the interests of time. Another cool thing is if you know it's a decomposition reaction and I give you the reactant, you should be able to tell me what the products are if it's a binary compound. Okay, that might be a new word for you. If it's a binary compound, bi means 2. So it means it's made of 2 different elements. So water would break down into hydrogen and oxygen. But again, you can't just write them down. You got to think about it. Hydrogen's a diatomic, oxygen's a diatomic, and then we would go back through and balance. Okay, so far reaction types, you have synthesis, putting 2 things together or more things together to make one. Decomposition is the opposite. Take one thing and break it down into its parts. Easy. Where this gets a hair more complicated, it's not too bad, is the next reaction type. It's called a single replacement reaction. Single replacement reactions, okay, you are replacing something. That's the kicker, single replacement, and you're replacing one thing. Your reactants must be a single element, now it can be diatomic, but that still counts as a single element, and a compound. All right, we're going to keep this simple, sodium plus potassium chloride. Your products are going to be a different element and a different compound. And I always kind of joke and say, like, this is your home wrecker situation. Because what's happening is sodium is jumping in here, pushing potassium and saying, potassium, you're single now. And now sodium and chlorine are in a little relationship, and poor potassium is all by himself. It's very sad. There's actually an animation on the PowerPoint. You should watch it. It's pretty epic. But that is a single replacement. Here's the kicker. The kicker is not everything can replace everything. So for example, in this one you guys are just looking at, sodium can connect with chlorine because sodium's a positive and chlorine's a negative. But you couldn't have the situation where, let's say, chlorine was by himself and sodium and potassium got together. That doesn't work. They actually can't do that. They're both positives. So we need some kind of rule to follow with single replacement reactions. So what you guys have to remember is that metals replace metals. Okay, positives replace positive, metals replace positives replace positives, metals replace metals. So if you have aluminum plus copper sulfate, okay, I've got to look at this and go, okay, if I look at the periodic table, aluminum is a positive, he's a metal. Copper's a positive, okay, sorry about that. And then sulfate over here is a negative. Remember, sulfate's one of your polyatomic ions. So I know that when these kind of come together in a single replacement, it's the aluminum and the copper that can switch places. Okay, metals can replace metals. So you would end up with copper on his own, okay, and aluminum matched up with sulfate. And of course, you've got to rethink the crisscross. When aluminum and sulfate come together, aluminum is a 3, sulfate's a 2, so you always have to rethink that. That's a single replacement reaction. Metal replaces metal. Now, the other thing you have to think about is you have to think about water. Okay, water can be kind of tricky, and this is true when you're balancing as well. You guys know water is H2O, but it's actually sometimes easier to look at it as HOH, a hydrogen and a hydroxide. If you do that and you put sodium plus HOH, all of a sudden, it's really obvious what's going to happen in a single replacement. Sodium's a positive, hydrogen's a positive, hydroxide's a negative, so it's these two that will swap places. My hydrogen is now flying solo, as much as he can because he's diatomic, and my sodium and my hydroxide end up combined. Those are single replacement reactions. One thing replaces another. Because things are actually complicated, there's another catch. You'll notice in the PowerPoint, there is something called the activity series. Now, let me just tell you, first of all, you do not have to memorize this, so don't stress about this. The activity series lists metals from most active down to least active. Okay, and again, you don't have to memorize it. It'll always be provided to you if you need it. So this is the beginning of it. This is just the first 7 elements on there. The kicker here is more active can replace less active, but you can't go the other direction. In other words, you can replace something that's beneath you on the list, but not something that's above you. The example I always use in class is think about a group project. Okay, if you guys have a group project and somebody walks up and says, hey, can I join your group? And you say, well, we'd have to kick somebody out. And you'd say, yeah, but if you kick your friend out, I will show up every day with cookies, with B-dubs, every study group. I get straight A's. I'll do most of your work, and I'll give you all the credit. Don't you want me in your group? Most of you are going to be like, see you later, friend. Wish I knew you better. Bye-bye. Bring in the beat-ups. However, if the ultimate slacker comes in and says, well, dude, can I be in your group? I'm not going to do anything. I'm just going to take credit for all y'all's work, and I smell bad, and I fart constantly. You're not going to want them. So you can replace something that is beneath you on the list, but not above you on the list. All right, so let me put this together and show you what I mean. If we had aluminum and hydrochloric acid, okay, looking at the activity series, which I realize you can't see the whole thing, so let me just fill in a couple more pieces, F, E, P, B, H, there we go. If we had aluminum plus hydrochloric acid, the question I would ask you is, can this reaction even happen? Can aluminum even bump hydrogen out of the way to bond with chlorine? So what we do is we find them on the list. There's my aluminum, there's my hydrogen. Since aluminum is higher on the list than hydrogen, it can take its place. So yes, this reaction can absolutely occur. Hydrogen would be flying solo, aluminum and chlorine would come together. And of course, you have to re-crisscross them, and then you would have to rebalance. Always, always, always. Another example, let's say we're looking at lead combining with potassium chloride. And the question becomes, can that reaction happen? Well, you go over to your activity series. Okay, here's lead right here. Here's potassium up there. So the reality is, no, that reaction can't even happen. If you put lead and potassium chloride together, nothing is going to happen. Just because you put two chemicals together, it doesn't mean they're going to react. And whether or not they react is all based on that activity series. Okay, so that's something we look at with metals, is can one replace the other? One thing we haven't talked about with single replacement yet, though, is what about nonmetals? Nonmetals can also go into single replacement reactions. Cool thing is you don't have to worry about any kind of activity series or anything like that. So if you're looking at fluorine and hydrochloric acid, okay, it's really simply just like the metals were, who replaces who. And nonmetals replace nonmetals just like metals replace metals. So fluorine is a negative charge, hydrogen is a positive, chlorine is a negative. So if we rework this, chlorine ends up being solo, whereas hydrogen and fluorine come together and they make the new bond. It's the negative and the negative that are switching place, or the positive and the positive. Okay, single replacements kind of has a lot of things to think about, but the format is always the same. It's always an element plus a compound, and you end up with a new element and a new compound. All right, that's the long one. Moving on. Couple more types. All right, next one we'll talk about is double replacement. This is what I constantly refer to as prom, and you will understand that analogy in just a minute. So in a double replacement reaction, clearly two things are replacing each other. Your reactants have got to be compounds, okay? Compound number one, compound number two. They both must be compounds. They can either be ionic compounds or acids. We haven't gotten real into that, but generally just remember they have to be compounds. The kicker here is the positive ions are going to switch places. So I jokingly call this prom because, you know, this guy comes in with a red tux, and this girl comes in with a red dress, and this guy comes in with a green tux, and this girl comes in with a red dress, or sorry, green dress, so everybody is all matchy. At the end of the night when people are leaving, you're like, why's that red tux leaving with that green dress? Because people done switch dates on the dance floor. You know that it happens. That's a double replacement. So how do I know what switches? The positive switch places. So I look at my periodic table. Sodium's a positive, hydroxide's a negative. Iron's a positive, chlorine's a negative. So my sodium and my iron, these guys are going to swap places. So what I'm left with is iron hooking up with hydroxide and sodium hooking up with chlorine. But remember, you can't just put them together. You've got to re-crisscross every single time. Okay, so all I've done is put the Fe and the OH together, but I had to remember iron's a 3, hydroxide is a 1. I knew iron was a 3 because of that right there. Okay, sodium and chlorine. That 3 from this chlorine did not translate to down here because it's different. Okay, chlorine's a 1, sodium's a 1, we put them together, and then of course we got to balance the whole thing. Okay, so those are double replacement reactions. That's prom. All right, last two. These are easier. Okay, combustion. For those of you that are pyros, you are familiar with this. Combustion means blowing stuff up. That's what this is. So we will take a hydrocarbon for a combustion reaction. And I bet if you think for 5 seconds, you can figure out what a hydrocarbon is. It's made of hydrogen and carbon. Ha-ha. In some kind of ratio. It could be C2H6, it could be CH4, whatever. A hydrocarbon is going to be the first thing. In a combustion reaction, there's one thing you have to add, and that is oxygen. Anybody that knows anything about fire knows you cannot burn anything without oxygen. So your combustion reaction will always start like that. A lot of people mistake it for a single replacement. Here's the kicker. If it is what we call a complete combustion means the entire thing has burned. This is very rare. Your products would be CO2 and H2O. That is smoke and that is steam. Okay, that means no ashes, nothing. That fire has to burn hot enough and fast enough to totally get rid of everything. No charring, no nothing. Doesn't happen much, but that's a complete combustion. If I took the same compound and let's just say wasn't enough fuel, wasn't hot enough, you get what's called an incomplete combustion. And an incomplete combustion ends with carbon, that's your ashes, carbon monoxide, that's your smoke, and steam. Now, truth be told, in the real world, sometimes part of something completely combusts and another part of something incompletely combusts. So you see a mix of this in the real world. It's not really one or the other, but we name the two reactions differently. All right, last one. You guys have done good. Last reaction type is called a neutralization reaction. Okay, a neutralization is actually a type of double replacement. So if you look at it and you're like, dude, that looks like a double replacement. It is a double replacement, but it's a specialized type. What happens in a neutralization is you get an acid and a base that come together. Now we're going to learn more about this later this year, but acids generally start with H, so like HCl. Bases generally end in OH. Okay, so if you see that beginning H and that end OH, that means you've got an acid and a base. When they come together and they neutralize, they're basically canceling each other out. So you end up with a salt of some sort, and remember from the ionic chapter, salt can be any ionic compound, and you end up with water. So in this example I gave you, the salt is the one you're most familiar with, sodium chloride and water. So yeah, that's a double replacement. But if it's an acid and a base, it has a special name, and we call it a neutralization. So one of the things you guys are going to have a lot of practice work to do on, and you hopefully can get a better start on it now, is identifying types of reactions. It's huge on the SOL, so take the time, go over them, make sure you can knock them out.